to two projects. In this video, we are going to explain about the project, which is deepfake audio detection via MFCC features using machine learning. Coming to the introduction of the project, deepfake audio refers to a synthetic audio content that is created or altered using artificial intelligence techniques to mimic real voices or generate speech that appears authentic. These techniques involve the manipulation of audio recordings to either generate entirely new content or modify existing recordings, making it difficult to discern between genuine and fabricated audio. In this project, we aim to address the challenge of detecting deepfake audio using machine learning and deep learning approaches. With the advancement of AI technologies, deepfake audio has become increasingly realistic and posing significant risk to various applications such as misinformation, fraud, and privacy breaches. Detecting such manipulated audio is crucial for safeguarding against potential harm and maintaining trust in audio based communication channels. Traditional methods for detecting audio manipulation often rely on manual inspection or basic signal processing techniques. However, these methods are often inefficient in identifying sophisticated deepfake audio due to their increasing complexity and realism. Moreover, traditional approaches may struggle to keep pace with the rapid evolution of deepfake generation techniques, leading to limitations in their effectiveness and scalability. The proposed system leverages machine learning and deep learning algorithms to overcome the limitations of traditional methods in detecting deepfake audio. Specifically, we utilize mel frequency capsule coefficients, which is MFCCs. This technique is to extract relevant features from the audio data. Additionally, we employ the fake audio dataset, which encompasses various sub-datasets based on the audio length and bitrate, providing a comprehensive benchmark for evaluating detection performance. Machine learning and deep learning play a crucial role in this field by enabling automated detection of deepfake audio. ML techniques such as support vector machine and gradient boosting allow for the classification of audio data based on extracted features, facilitating the differentiation between genuine and manipulated recordings. Coming to deep learning models such as BGG16 excel in learning complex patterns and representations detecting directly from raw audio data, thereby enhancing the detection capabilities of the system. Objective of the project. The aim of the project is to develop a system that is capable of detecting deepfake audio, thereby mitigating the risks associated with the spread of fabricated or manipulated audio content, such as misinformation, fraud, and breaches of privacy. The goal is to employ a variety of algorithms, including support vector machine, multi-layer perceptron, decision tree, extra tree, logistic regression, Gaussian naive Bayes, ADA boost, gradient boosting, XGBoost, linear discriminant analysis, which is LDA, quadratic discriminant analysis, VGG16, long short-term memory networks, and convolutional neural networks to accurately detect deepfake audio. The aim is to classify audio samples into two classes, which is fake, indicating manipulation or fabrication, or genuine, which is indicating authenticity. The objective is to compare the performance of the various algorithms using evaluation metrics such as accuracy, precision, recall, and FN score. These metrics provide insights into the effectiveness of each algorithm in correctly identifying and classifying fake and genuine audio samples. The goal is to benefit various stakeholders, including media organizations, law enforcement agencies, social media platforms, and general public. By enhancing the detection of deepfake audio, the project aims to improve the trustworthiness, credibility, safety, and integrity across various sectors and communities. To implement this project, we need software and hardware requirements. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, backend framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. And the hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement this project, we have designed various steps in the flow of work. So coming to the first step, which is importing the packages. This step involves importing necessary Python packages or the libraries that are required for data processing, visualization, modeling, and web development. For example, we have imported pandas for data manipulation, matplotlib and seaborn for visualization, scikit-learn for machine learning, TensorFlow for deep learning, Flask for web development, SQLite for database management. The next step is exploring the dataset. This step involves exploring the dataset to understand its structure, characteristics, and content. It includes examining different subsets of the data, such as Second segments, which is 2 seconds, normalize data, original recordings, and re-recorded audio to gain insights into the dataset's properties. Coming to the next step, which is data visualization. Data visualization techniques are applied to gain a better understanding of the dataset's distribution, patterns, and relationships. This involves plotting wave plot, spectrogram to visualize various aspects of the audio data. The next step is bit conversion. This step involves performing various transformations on the audio data to prepare it for analysis and modeling. This includes adding random noise to the input audio data, stretching or compressing the input audio data in time, shifting the audio data along the time axis by a random amount, changing the pitch of the audio data, increasing and decreasing the speed of the audio data. These transformations help augment the dataset and improve model robustness. Coming to the next step, which is feature extraction. Feature extraction involves extracting relevant features from the audio data that can be used for model training. The techniques which are used are MEL frequency, capsule coefficient. Coming to the next step, which is data preparation. The data is pre-processed and formatted to ensure compatibility with the machine learning model. The next step is splitting the data into train and test. The dataset is divided into training sets and the testing subsets. The training data is used to train the machine learning model, while the testing data is used to evaluate its performance and generalization ability. The next step is building the model. Here, machine learning models and deep learning models architectures are defined. This involves defining the model layers and configuring hyperparameters. Training the model. The model is trained on the training data using optimization techniques such as gradient descent or stochastic gradient descent. The training process involves adjusting model parameters to minimize a predefined loss function and improve predictive performance. The next step is Flask framework with SQLite for sign up and sign in. Flask, a web framework for Python, is used along with SQLite, which is a lightweight relational database management system, to implement user authentication features such as sign up and sign in. This allows users to create user accounts, securely authenticate themselves. User upload image for analysis. Users can upload audio files for analysis through the web interface. This involves creating a user friendly interface for file upload and implement backend logic to handle file processing. The next step is the given input is pre-processed. The uploaded audio file undergo pre-processing steps similar to those described earlier to prepare them for analysis by the trained model. This ensures that the input data is properly formatted and transformed for compatibility with the model. The next step is trained model is used for predicting the result. The pre-processed audio data is fed into the trained machine learning or deep learning model for prediction. The model generates predictions based on the input features and returns the predicted outcome, such as whether audio classified as genuine or fake. The last step is final outcome is displayed. The predicted outcome is displayed to the user through the web interface, providing insights into the authenticity of the uploaded audio file. This allows users to make informed decisions based on the analysis results. Algorithms which are used for deepfake audio detection are support vector machine, which is SVM. It is a supervised learning algorithm used for classification and regression tasks. It finds the optimal hyperplane in an n-dimensional space that best separates data points of different classes. It is commonly used for binary classification tasks, such as distinguishing between genuine and fake audio samples. It is effective in handling high dimensional data, and it can capture complex relationships between features. The next algorithm is multi-layer perceptron. It is a type of artificial neural network with multiple layers of nodes, which are neurons, including an input layer, one or more hidden layers, and an output layer. Each neuron is one layer, which is connected to every neuron in the next layer. MLP is well suited for nonlinear classification tasks, and it can learn complex patterns from the data. It is suited and it is used in the project for its capability to capture intricate relationship between audio features and classify deepfake audio accurately. The next algorithm is decision tree. It is a tree-like model where an internal node represents a feature, the branch represents a decision rule, and each leaf node represents the outcome of a classification or regression task. It is used in the project for classification tasks due to its simplicity, interpretability, and ability to handle both numerical and categorical data. They can effectively capture features, intricacies, and provide insights into the feature importance. The next algorithm is extra tree, which is extremely randomized trees. It is an ensemble learning technique that builds multiple decision trees and combines their predictions. It introduces randomness in the feature selection process and splits nodes based on their random thresholds. Extra trees are used for classification tasks in the project to improve model performance and reduce overfitting. They are particularly beneficial when dealing with the noisy or high dimensional data, and it can provide robust predictions. The next algorithm is logistic regression. It is a statistical model used for binary classification tasks. It models the probability that a given input belongs to a particular class using the logistic function. Logistic regression is used in the project for its simplicity, efficiency, and interpretability. It provides probabilistic outputs and it can handle both linear and nonlinear relationship between features. The next algorithm is Gaussian naive Bayes. Gaussian naive Bayes is a probabilistic classifier based on Bayes' theorem and assumes that features are independent for each other given the class label. It models the likelihood of a feature given the class using Gaussian distributions. It is used for classification tasks in the project, especially when dealing with the continuous valued features. It computationally efficient and robust to irrelevant features. The next algorithm is AdaBoost, which is adaptive boosting. It is an ensemble learning technique that combines multiple weak learners to create a strong classifier. It iteratively adjusts the weights of misclassified samples to focus on difficult to classify instances. AdaBoost is used in the project to improve classification accuracy and reduce bias. It is particularly effective in handling imbalanced datasets and it can adapt to complex decision boundaries. Coming to gradient boosting, it is an ensemble learning technique that builds a series of decision trees sequentially, where each tree corrects the errors of its precedor. It minimizes a loss function by adding weak learners in a greedy manner. Gradient boosting is employed in the project for classification tasks due to its simplicity, ability to handle heterogeneous features, nonlinear relationships, and complex data distributions. It typically achieves high predictive performance and it can capture intricate patterns in the data. The next algorithm is XGBoost, which is extreme gradient boosting. It is an optimized and scalable implementation of the gradient boosting. It introduces regularization techniques and parallel computing to improve model performance and the speed. XGBoost is utilized in the project for its efficiency, scalability, and superior performance in the classification tasks. It is known for its robustness against overfitting and ability to handle large datasets with high dimensionality. The next algorithm is linear discriminant analysis, which is LDA. It is dimensionality reduction technique and a classification algorithm that seeks to find the linear combinations of the features that best separates different classes in the data. LDA is used in the project for dimensionality reduction and feature extraction, particularly when dealing with multi-class classification tasks. It aims to maximize the separation between classes while minimizing intra-class variance, making it effective for classification. The next algorithm is QDA, which is quadratic discriminant analysis. It is a classification algorithm similar to LDA but relaxes the assumption of equal covariance matrices across classes. It estimates separate covariance matrices for each class. QDA is utilized in the project for classification tasks when the assumption of equal covariance matrices is not met. It provides flexibility in modeling nonlinear decision boundaries and capturing complex relationship between features. Coming to VGG16, which is Visual Geometry Group of 16, it is a deep convolutional neural network architecture consisting of 16 layers, including convolutional layers, max pooling layers, and fully connected layers. It is widely used in image classification tasks. VGG16 is adapted for the project to process audio data by converting spectrograms or the other representations of the audio into image like inputs. It is utilized for feature extraction and classification in the conjunction with transfer learning techniques. The next algorithm is LSTM, which is long short term memory. It is a type of recurrent neural network architecture designed to model sequence data and capture long term dependencies. It incorporates memory cells and gating mechanisms to retain and selectively update information over time. LSTM is employed in the project for sequential data modeling, particularly in tasks involving time series data or sequential audio signals. It is effective in capturing temporal dependencies and patterns in audio sequences. The last algorithm is convolutional neural network, which is CNN. It is a deep neural network architecture commonly used for image processing tasks. It consists of convolutional layers, pooling layers, and fully connected layers, which extract hierarchical features from the input images. CNNs are adapted for the project to process spectrogram representations of the audio data, treating them as a two-dimensional images. They are utilized for feature extraction and classification, leveraging their ability to capture spatial patterns and hierarchies in the audio features. We have used accuracy, precision, recall, and FN score, which are the performance metrics to evaluate all the classification models built in the project. So here, We have the performance comparison graphs for the dataset, which is for 2 seconds dataset. This is the accuracy comparison graph where x-axis represents all the algorithm names and the y-axis represents the accuracy score. Similarly, we will have for other graphs also. Now we will know what is accuracy. Accuracy is the proportion of the correct predictions in a classification task, measuring the overall correctness of the model predictions. This is precision comparison graph. Precision is the ratio of true positive predictions to the total positive predictions, representing the model's ability to correctly identify relevant instances while minimizing false positives. This is recall comparison graph. Recall is also known as sensitivity or true positive rate. It is the ratio of true positives to the total actual positives, measuring a model's ability to capture all relevant instances without missing any. This is F1 score. The F1 score is the harmonic mean of precision and recall, offering a balanced measure that considers both false positives and false negatives, making it suitable for imbalanced datasets. Here we have performance comparison graphs for the dataset, which is for normalized data. And this is for original data. And this is for re-recorded data. The algorithm which performs well among all these metrics will be used for final prediction. To execute the project, first we have to open the code folder which contains source code files. This is the code folder of the project. This is the dataset folder in which we have all the 4 datasets. We use all these 4 datasets for training the algorithms. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. This is the model file, which contains the algorithm information and that will be loaded into the project code during runtime. And these are the notebook files, which are the notebook IPYNB files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And these are the other model files. This is the signup file. This file is the database file used to store the user information. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we have to open Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. Here we can see that current directory is changed to the code folders directory. Here we need to type the command python space app.py to compile the app.py file. And now we need to click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. This is the local host and this is the port. Now we have to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, which is displayed in the browser. This is built by using the Flask framework. Here, first we need to click on sign up and enter all the registration details and click on sign up. I have already signed up and have an account in it, so I'll directly sign in. For that, click on sign in button. Here we need to provide our credentials, which are the username and the password. So I'm giving my username and the password. Now click on sign in. We have signed in successfully and we are redirected to prediction page. As we have already told you that we are using 4 subsets of data sets, which are for 2 seconds, for normalized data, and for original data, and for recorded data. Now we will be doing prediction for all these 4 data sets. So first we will do the prediction for 2 seconds data set. So click on for 2 seconds data set button. And here we can see a choose file button. We need to click on that for uploading the audio files. So I'm clicking on choose file button. From the folder I'm selecting the first audio file and now click on Open and now click on Upload. So here we got the output result that output for the uploaded audio sample is fake audio sample detected, which means it is a deep fake audio. Now we will try with the other file. Click on Home. Click on for 2 seconds. Click on Choose File. This time I will upload the second audio file. Click on Open. Here we can see that audio is loaded. Now click on Upload. Here we can see that the audio is predicted as genuine audio, which is sample detected, which means that it is a genuine audio. Now we will try with the other audio. Click on Home. Now we will do the prediction for the other dataset, which is for normalized data. Click on For Norm. Click on Choose File. This time we will upload the third audio. Click on Open and now click on Upload. So here we got the prediction as the audio as genuine audio. Now we will try with the other audio. Click on Home. Click on For Norm. Click on Choose File. This time we will upload the fourth audio. Click on Open and click on Upload. So here we got the prediction, that is output for the uploaded audio sample is fake audio sample detected, which means that the audio is deep fake audio. Now we will try with the other audio and the other dataset. Click on Home. Now click on For Original because we are going to do prediction for the For Original dataset. Click on Choose File. This time we will select the fifth audio. Click on Open and now click on Upload. So here we got the prediction as output for the uploaded audio sample is fake audio sample detected, which means that it is deep fake audio. Now click on Home. Click For Original. Click Choose File. This time we will upload the sixth audio. Click on Open. Here we can see that audio is loaded. Now click on Upload. So here we got the prediction as the output for the uploaded audio sample is fake audio sample detected, which means that it is deep fake audio. Click on Home. Now we will try with the other dataset. Now we will do the prediction for recorded dataset. Click on this button. Click on Choose File. This time I will upload the 8th audio. Click on Open and now click on Upload. So here we got the prediction as genuine audio sample detected, which means it is not deepfake audio. Now click on Home. We will try with the other audio. Click on For Recorded. Click on Choose File. This time we will upload the last audio. Click on Open and now click on Upload. Here we got the prediction as the output for the uploaded audio sample is genuine audio, which is sample detected. Now click on Log Out. In this way, if we upload the audios to the system, then the system will detect whether it is genuine audio or it is manipulated. Conclusion of the project is the project effectively detects deepfake audio, meeting its primary goal through the application of machine learning and deep learning techniques. XGBoost, Decision Tree, and CNN demonstrate the strong performance, showcasing high accuracy, precision, recall, and FN scores. The optimized CNN algorithm is chosen for its ability to handle high-dimensional data and provide robust predictions, contributing significantly to the detection system's effectiveness. Potential improvements include exploring additional deep learning architectures, integrating advanced pre-processing methods, and extending capabilities to detect various audio manipulation techniques. Additionally, plans involve real-time monitoring and collaboration with experts for enhanced dataset diversity and system robustness.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.